big pleasure to have together with us today Lance Dixon. He's professor at SLAC, the Stanford Linear Accelerator Center, but he has been awarded research chairs and professorships, guest professorships in several other great places like at CERN, University of Cambridge, École Normale Supérieure, Perimeter Institute for Theoretical Physics, Humboldt University Berlin, ETH Zurich, and the University of Zurich. And his research is very broad, and it ranges from work about strings on orbifolds, his PhD thesis, up to precision calculations in QCD. And in fact, for his path-breaking contributions to the calculation of perturbative scattering amplitudes in QCD and Yang-Mills theories, he received a prestigious prize, the Sakurai Prize for Theoretical Particle Physics with Bernd Kosover in 2014. And his work continues being at this interface between phenomenology and more formal aspects in theoretical high-energy physics, such as multi-loop properties of gauge and gravitational theories. And today, he will speak about scattering amplitudes in maximally supersymmetric gauge theory and a new duality. Thanks a lot for being with us.
Thanks, Valentina, for that very kind introduction. It's really a pleasure to be able to speak at the GGI Tea Breaks. I've really enjoyed listening to them throughout the pandemic, and I'm grateful for the organizers for scheduling them as late as possible in European time, so I didn't have to wake up too early for them, although I confess sometimes it was still a little too early. But anyway, I would like to tell you a little bit about a sort of general program for constructing scattering amplitudes in the simplest gauge theory we know, maximally supersymmetric gauge theory, or what we sometimes call n=4 super Yang-Mills theory in the limit of a large number of colors. And so part of that will be maybe reviewing the general structure, but towards the end, I also want to tell you about a new mysterious kind of duality that we found between two types of things. And that phase and some of the earlier work too was done in collaboration with Omer Gurdegan, Andrew McLeod, and Matthias Wilhelm in a paper that came out in December. And I just want to give you a very short summary of what we found. So we calculated some stuff to about 7 loops, 6 gluon scattering, as exemplified by this Feynman diagram on the left. And then we found another problem where we could actually calculate even to 8 loops. And this is related to Higgs boson scattering amplitudes, as we'll discuss later. And then the really funny thing happened. We looked at these two things, which we had no right to believe were true, and we managed to find that they were in some sense almost exactly the same, but written backwards. And so I want to try to explain what it means to write something backwards and this mysterious relation between these two seemingly different quantities. So let's see if I can advance my slide now. Oh, there we go. Okay. So I wanted to put this a little bit in context, though, because it's also the reason I got into this area in the first place, which was the goal of trying to make more precise predictions for experiment. And in particular, for collider physics at the energy frontier, there is the Large Hadron Collider. And the Large Hadron Collider collides protons, and protons are bags of quarks and gluons. And when you collide them at very high energies, the most energetic events that you see coming out and the most copious events are those in which the quarks and gluons interact through quantum chromodynamics, scatter into each other, and they emerge from the collision point by materializing, strings breaking, and many hadrons being produced in a collimated fashion. And you look at many of these events and it's totally obvious that there's something underlying that produces these jets, and we understand that those are quarks and gluons. But to describe these processes with high precision, we need to work perturbatively and understand the perturbative expansions of the cross sections for that. And the underlying things that you need are scattering amplitudes. So let's give a simple example of this, which is the production of the Higgs boson at the Large Hadron Collider. Now, there are a few different ways you can produce the Higgs, but the most copious way, the largest cross-section, ironically, involves colliding two particles inside the proton, gluons, that don't even talk to the Higgs directly because they don't carry any electroweak charge. But they do couple to the top quark because it's colored, and they can produce a virtual TT bar pair where the tops don't even materialize into real particles, but inside this loop, they couple to the Higgs because the top quark has a large mass and it gets it directly from the Higgs through the large Yukawa coupling. So this is a leading order diagram. It's already a one loop diagram to produce the Higgs, but it's the most efficient way of producing the Higgs at the LHC. Now, because the top is so heavy, what we say is that it only propagates a very short distance. And so this interaction, although it looks like a loop with it propagating around, if you look at it from the outside, it's very short distance, and we can replace it by a local operator, and or maybe a series of local operators. But by far the most important operator, the leading one, is the operator that couples a Higgs to the pair of gluon field strengths like this. And the reason we can do this is justified by the fact that 2m top, which is the energy you need to make these guys for real, is much bigger than the Higgs mass, especially when you square it, as usually occurs. So we can simplify the calculation by integrating out the top and just using a local operator. But I'll just put this top loop in to remind you. And then this line shows that the cross section is the interference of an amplitude and a conjugate amplitude. So that was all leading order, but leading order is not good enough, as you can see from this plot. On the right here, this shows the result of a fantastic calculation that was completed back in 2015 by Anastasio, Dulat, Herzog, and Misselberger, where they calculated the Higgs cross section not to leading order, not to next to leading order, next to leading order, but to NNNLO. And what this shows is, as a function of the LHC energy, which has been at 7, 8, 13, now 14 TeV, what the probability of producing the Higgs is, or the total cross section. And this is the estimate from the leading order cross section if you vary some arbitrary scales in the calculation, but it's totally off. It's off by maybe a factor of 2.7. As judged by the highest order we've been able to calculate to. And things only really settle down so the bands don't move too much once you get to this very high order. So I showed you the processes that go into the leading order calculation. You just take this guy and square it, and also multiply by the parton distributions. But if you want to go to NLO, you have to combine two types of processes. One is the same process as before, where the two gluons fuse to a Higgs and nothing else, but now at higher order. So you trade, on one side, you trade the leading order amplitude for an amplitude that's one loop. If you treat this as a local operator, it has one gluon loop in it. But on the real side, you also have the possibility at the same order in perturbation theory, the same number of vertices of these gluons, you can radiate a gluon into the final state. So you can have the process glue goes to Higgs plus a gluon. And so this is squaring that sort of tree level process. There are more Feynman diagrams in each case, of course. This is just to illustrate. Anyway, when you do that, then you have to integrate over the phase space for this gluon as well. Now we'll skip NNLO and just go straight to NNNLO to illustrate the kinds of topologies that have to be done at the state of the art, the current state of the art. And you can see that now you need to add on the virtual side 2 more loops. So you have what we call the 3-loop Sudakov form factor for glue to Higgs. You also have 2-loop processes for glue to Higgs glue. 1-loop processes where you produce 2 gluons, and tree level processes where you produce 3 gluons. And there are many other Feynman diagrams, even just with gluons. Plus, you have to route quark lines through here in many different places, and take care of operator renormalization 1 over m top, higher powers than that, and convolute everything with the parton distributions for the quarks and gluons inside the proton. And so this was a really mammoth undertaking, and there are many technical ingredients to it. I just want to mention, though, that the underlying engines that you need for doing all this are the scattering amplitudes. And for example, this process here, glue to Higgs glue, you had to do it at 2 loops, and that was known somewhat earlier, as I'll mention shortly, but that's still the current state of the art in QCD. And you might wonder, you know, what are sort of the bottlenecks to going further in QCD? And one of the big issues is that you can draw the Feynman diagrams and get a computer. There are large numbers of diagrams, but it can be computerized pretty easily. But at the end of the day, you have to do integrals over all the virtual momenta, and for the total cross-section over the real momenta too. And those integrals can be very difficult. In contrast, if you just go back to the first subleading order in perturbation theory, or one loop, you find that in that case, no matter how many external legs you have, in 4 dimensions, if the momenta are all in 4 dimensions, all the integrals can be reduced to scalar box integrals. And so it was realized as early as the 50s that you could do this sort of thing. And then in like the 70s, the Tufton-Veltman showed that all those box integrals were really just combinations of one type of special function, the dilogarithm, where you integrate a logarithm with a separate d-log, a dt over t. And so only one type of function plus logarithms were really necessary to compute everything at one loop. But at L loops, you get special functions with up to 2L integrations. And there's a recent paper discussing this bound of 2L. And these special functions, well, we'll talk about some of them in the rest of the talk, but they're class of functions that can include iterated integrals. In some cases, they can be written as generalized polylogarithms. Sometimes you need other more complicated functions like elliptic polylogarithms. So in the general case, it's a very difficult problem to not just evaluate the diagrams, but to integrate over all the loop momenta. So now we're going to turn away from QCD and go to a simpler theory, which could be viewed as a toy model for QCD, although it's always a fair question of how much you learn from this toy model when you go back to QCD. We can talk about that later. But this model is planar n equals 4 Super-Yang-Mills theory. I'll define it shortly, but its structure is extremely rigid because of all of the supersymmetry, and there's a hidden integrability as well. Now, in general, just functions of various kinematic variables can be organized into dependence on the kinematics that is rational in nature, like a rational function of ratios of polynomials, and also special functions, transcendental functions, like these weight 2L functions we talk about. And in the QCD case, this decomposition tends to be extremely complex. And the advantage is that for planar n equals 4, we know that for many of these amplitudes, what the rational structure is. And so it's sort of dictated once and for all. You sort of see it at one loop, and then it doesn't change anymore. And so you can really focus on what the transcendental functions are. In fact, in this talk, I'll never really say much about the rational structure, but the cases I'm talking about, it's very trivial. It's just some overall prefactor that you could see at tree level. So instead, we're going to focus on these transcendental functions. Another great thing about planar n equals 4 is that at least 3 dualities have been observed to hold. And one is ADS-CFT, which is a very general duality, which many of you have seen many times before. In the specific context of scattering amplitudes, through the use of ADS-CFT, it was argued that amplitudes are actually dual to Wilson loops. And I'll come back to that later. And then we've observed this strange duality, which we really don't understand the physical underpinnings of it yet, but I'll tell you more about it through the course of this talk, that relates amplitudes where you scatter only gluons, 6 of them in particular, and form factors, which involve operators similar to the operator that produces the Higgs boson at the LHC. So there are these 3 features that help us understand how to elucidate the structure of scattering in planar n=4 super Yang-Mills theory. Another interesting aspect of this theory is that unlike QED and QCD, its perturbative expansion actually converges. It has a finite radius of convergence. And in many other theories, the perturbative expansion is often expected or known to be asymptotic. But the reasons why it's asymptotic are typically renormalons, which have to do with various large order growth in the coefficients that are proportional to the beta function. But n=4 super Yang-Mills is a conformal field theory. The beta function vanishes. And so we don't have any renormalons. And secondly, instantons can also cause asymptotic factorial growth and non-zero radius convergence. But instantons typically go like e⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ hold fixed NC times G Yang-Mills squared, or the 't Hooft coupling. And in terms of that, the instanton effects are exponentially suppressed and go to 0 as we take NC to infinity. So these reasons why you have asymptotic series or non-zero radius of convergence don't hold in planar n equals 4. And in the cases where for observables where we know the radius of convergence, it tends to be always finite. And in fact, for one important quantity called the cusp anomalous dimension, which is very closely related to amplitudes, the exact solution of Beisert, Eden, and Staudacher back in 2006 shows what the radius of convergence is. And in units that are popular, where we call this lambda over 16 pi squared, the coupling G squared, the radius is 1/16 in G squared. Another way of saying that is that the ratio of successive loop orders for the cusp anomalous dimension asymptotically goes to -16. And we can take ratios like this for scattering amplitudes when we compute them, and we can see the same radius of convergence emerging. So that's another interesting lesson, and it's an indication of how close we are to the asymptotic behavior of the loop amplitudes when we get to high loop orders. I'll try to come back to that at the end too. But first, let's go back and discuss what n equals 4 super Yang-Mills, what the theory has in it. And it has the same massless spin 1 gluon that's present in QCD. Instead of having massless quarks in the fundamental representation of the gauge group, SU3 or SUNC as we'll generalize it, it has 4 massless spin 1/2 gluinos and 6 massless spin 0 scalars. And these are all in the same supermultiplet. And if we work with on-shell states of definite helicity, where the particles are all massless, there are on-shell SUSY generators that change the helicity by 1/2 unit. But you can't use them twice. In this case, they square to 0 and they anti-commute. So you can only use them 4 choose 2 times, and the anti-symmetric combinations are these scalars, whereas using them once, you get the gluinos with helicity 1/2 from helicity 1 gluon. So if you use them 4 times, you get all the way down to helicity -1. So since everything's in the same supermultiplet, you can imagine that the supersymmetric word identities are very powerful, and they are. Now, QCD has quarks instead of the gluinos, but the kinematic structure of the interaction is just the same. It's still the Dirac gamma matrix, and there's just a little bit of color algebra between these two. So they're really very similar. But of course, you also have these scalars, which you don't have in QCD, and they have Yukawa couplings with the fermions, which cause differences. But at tree level, those differences for n gluon amplitudes totally go away, because the interactions of the gluons with fermions and scalars always require you to pair produce them. And if you have to pair produce inside a diagram that has only gluons on the outside, and you make a pair, you're going to have to destroy it. And that means that you get loop amplitude. So the tree level gluons in QCD are really the same. And you can prove the same identities, and this was realized way back in the 80s, that the QCD tree amplitude obeys all identities of n=4 supersymmetry. And those include statements like if all the gluons have plus helicity or just one has minus, you get 0. And the two that have negative helicity only depend on the negative helicity location in a very simple way. And this is part of the essence of the so-called Park-Taylor or maximally helicity violating amplitudes. But all these things change at the quantum level, at the loop level. And for example, in the n=4 case, you cancel a lot of loop momenta in the numerators of Feynman diagrams. And at the end of the day, at one loop, you basically have only scalar box integrals surviving. And those scalar box integrals are the dialogues we talked about before. They're actually all weight 2 functions. So you have done 2 different integrations. Like a logarithm has weight 1, and here there are 2 logs, or you can integrate a log and get a dialogue. So the basic structure of this glue to Higgs gluon amplitude at one loop sort of looks like this in the n=4 analog of it. The QCD one has a very similar structure, but it also has other pieces which have lower weight or lower transcendentality. And they come from some various other integrals that contribute that don't have the supersymmetric cancellations. For example, you can get a bubble integral or some of these triangle integrals whose logarithmic part is this single log. And this persists for many processes and to higher orders in perturbation theory as well. And the general statement is, and I don't think there's really any counterexample to this, that in the n=4 case, the amplitudes have a uniform weight at loop order L, which we'll define a little more carefully later, but it's always 2L. So it roughly corresponds to 2L non-trivial integrations. So the logarithm has one integration of a rational function, dt over t, or d log of t. That's just the definition of the logarithm, and we assign it weight 1. And other examples of functions are the dilogarithm we talked about that has an extra integration, so we give it weight 2. And then the n-fold polylogarithm is defined by integrating the n-1 one by an extra d log, which adds one more to its weight. So it's a weight n function. But we need much more general functions than these so-called classical polylogs to describe high loop order scattering amplitudes. So I wanted to mention now one of the key dualities that is a property of n=4 Super-Yang-Mills, or it maps n=4 Super-Yang-Mills and more generally conformal field theories to theories of gravity in anti-de Sitter space. And in the case of n=4 Super-Yang-Mills specifically, it's dual to string theory propagating in 5-dimensional anti-de Sitter space across a compact 5-sphere. And the symmetries of the anti-de Sitter space include our SO4, 2, and that's much bigger than SO3, 1 for a generic theory, but a conformal theory has the extra 5 generators that go into making up SO4, 2. So many of you, of course, know all this. And the feature of ADS-CFT as a duality is that it's a weak, strong duality. In the regime where the gauge theory is strongly coupled, G-Yang-Mills is large, or lambda is large even, you have a simpler situation on the gravity side. Whereas when G-Yang-Mills is weak, the other side, the string theory side, is very hard to deal with generally. Now, string theory has another symmetry because it has a world sheet that can be parametrized by 2 variables, sigma and tau. And it's possible to consider exchanging the roles of sigma and tau. So if you expand out the coordinate of the string x mu, which depends on these 2 variables, sigma and tau, And if the string tension is large compared to the scales of interest, you have small fluctuations of the string around its center of momentum, k mu. And k mu is the coefficient of the world sheet time, so that the momentum that you get by taking a tau derivative is k mu. But you could also, for a given process, consider exchanging the roles of sigma and tau. And when you do that, then the string now stretches a distance proportional to k mu as you go from one end of it to the other. So instead of looking like a little short string, it's stretched fairly tightly. The oscillator contributions are small, and those also depend on tau and sigma, of course. So in that configuration, the string becomes the boundary condition associated with an incoming string becomes this almost light-like straight line. And that led to a picture developed by Aldai and Maldacena and illustrated here by Amit Sever, in which the strong coupling picture of gluon scattering, or states of strings with these light-like momenta, is described by a world sheet that has a boundary, which is a closed light-like polygon. So each of the line segments corresponds to a different incoming or outgoing gluon, and the light-like momenta add up to 0 because of momentum conservation around this base here, out at infinity. And then in the center of the scattering process, the holographic direction, which characterizes what distance scale things are happening at, the world sheet has to go inside. And so you actually have at the semi-classical or strong coupling level a minimal area problem that describes the scattering amplitude. You need to compute the area of this minimal area surface. And interestingly, there's lots of techniques from classical integrability that let you do this. And as I said, the boundary is determined by the kinematics, it's determined by the momenta of the gluons. This picture also led to a remarkable discovery at weak coupling, which is that the same sort of picture holds, but instead of doing a string calculation with a smooth world sheet, you sort of imagine that at weak coupling, this is given by a web of gluons, and at very weak coupling, only a couple of gluons being exchanged among this light-like contour. And that's exactly what you would get if you constructed the expectation value of a closed Wilson loop. As you expand that expectation value in perturbation theory, you fill this loop with gluons. And so it was realized around the time of Aldai and Maldacena's paper that you could do calculations 2 different ways, both at weak coupling, and get the same answer. And so this was verified in many processes, and there are also some general arguments given. So in space-time, you deal with these gluon momenta, but in the dual space-time, it's more natural to consider where the corners of these polygons are. And in order to do that, you need to introduce what we call dual momenta, whose differences give us back the gluon momenta. So the edges between the vertices are the momenta, and the vertices are characterized by some new dual variables. And these variables really live in kind of a position space through the T duality, and they transform like positions under a conformal symmetry, which is called dual conformal symmetry when viewed in terms of the space-time scattering process. So this duality was verified to hold at weak coupling, and it's basically one of the underlying assumptions in going forward. This symmetry is quite powerful. It reduces the number of kinematic variables in the process by 5, 1 for dilatations and 4 for special conformal transformations. The special conformal transformations can be viewed as inversions and translations. Well, one inversion, a translation, a small one, another inversion. To demonstrate the invariance, you just need to ask that the process is invariant under the inversion. If you only make it up of translation and Lorentz invariant quantities. So these differences of positions are can be rewritten using this relation between the x's and the k's, and they are Mandelstam variables, these xij squareds. But under the inversion, they transform in this way, and xij squared picks up a factor of xi squared xj squared. This is all very familiar to conformal field theorists, that the way you write down dual conformally invariant functions is to write down these cross ratios, u, I, j, k, l, where we swap the j and the k in the middle. And so these functions are automatically invariant because when you apply this transformation, you get an xi squared, xj squared, xk squared, xl squared, all of which cancel. Now, in contrast to what you do in position space conformal field theory, here we have a further constraint that the adjacent xi j squareds, where j is I plus 1, they vanish because they correspond to these light-like momenta. And because of this constraint, we actually have no variables for n equals 4 or 5. And for n equals 6, we get exactly 3 of them. So the first non-trivial case is the 6 gluon scattering, which is sort of the mystery of why did I pick 6 to discuss. And it's the first case that depends on a non-trivial number of variables. And we can write them down, and they involve, we're not allowed to use any of these edges of the hexagon. We have to use interior chords, but we can have x1 3 squared and x4 6 squared in the numerator and x1 4 squared, x3 6 squared in the denominator, as illustrated by these solid and dashed lines. And this is essentially one of the 3, and the other 2 are just obtained by doing cyclic rotations using the symmetries of the hexagon. So we have these 3 variables. In the 7-point case, we would find 6 of them. And in general, there are 3n minus 15 of these ratios, or 5 fewer than you would have written down in the case of without this symmetry. So 3 variables is actually quite a lot. It means that the phase space has a very complicated structure, and there are many interesting limits inside here. And we can use this richness to not only put constraints on the functions in order to determine them by bootstrapping or from scratch, but we can also investigate these limits. And I'm not going to go through all of these limits here, although I'll mention a little bit about the near collinear limit and the origin later. But we can explore many of these different regions for the 6 gluon process and its dependence on these 3 kinematic variables. So we've been engaged in trying to refine a bootstrap for going to higher loops for this problem for about a decade now. And we've been able to push successively to higher loop order. And we embed all of the functions that describe these 6 gluon amplitudes in the same space, which we call the hexagon functions. And we learn more about it each time we get to the next order. And because everything's sort of embedded in the same space, we have a more unified way of doing the perturbation theory, which we hope will lead to a sort of finite coupling description eventually. I'll come back to that in a second. But at 7 loops, you can try to count the number of Feynman diagrams, or guess or estimate if you don't want to count it. But there's probably something like 1 billion Feynman diagrams that get subsumed into these 7 loop results. And because of all these different variables, we have a huge theoretical data mine that we can look at and try to find patterns. And one of the patterns that we found recently is this duality when we connect to form factors. Here's an example of a numerical result that you can get. It's a finite piece of the amplitude that we call the remainder function. I'm not going to go through the details of the definition, but it was computed at strong coupling using this minimal area prescription back in 2009 by Alday, Gaiotto, and Maldacena. And we computed each order in perturbation theory. And I should stress that these curves here are not some cumulative thing through 7 loops. They represent the individual loop order coefficients. And there's a remarkable similarity in shape as you go down here. And there's very similar behavior so that you can hardly even see it on this plot between the different loop orders when you're down in this region. Out here, they differ more. But when you see these things numerically, it leads you to explore and look further at what's going on down here where U goes to 0. So we took that as a clue, and we tried to understand the analytic behavior when U was going to 0, and also V and W. And we found something kind of interesting. We looked at the behavior as U went to 0 through 7 loops. And we found that it was for this remainder function, and also for a very closely related quantity, the log of the amplitude with some stuff subtracted off, we found that they were all quadratic in logarithms through 7 loops. And because they're quadratic in logarithms, and because the overall transcendentality grows with the loop order, the coefficients at each loop order were Riemann zeta values. And you can see some examples through 5 loops of what these coefficients are of this term, which we called gamma oct, and this one, which we called gamma hex, and some constant term. And even more interestingly, these coefficients could all be understood in a paper with Benjamin Basso and Yorgos Papathanasiou. We understood that these coefficients were all computable in the same way as the cusp anomalous dimension, except for one small tilt angle. And so the cusp anomalous dimension becomes a special case where we set this angle to pi/4, whereas these two correspond to setting it to other angles. And so that's an example of sort of, discovering something because you just stare at a plot for a while. And, but more generally, what we hope to do is to be able to go to finite coupling. This is an example of something which we now have finite coupling expressions for, that we can interpolate all the way from weak coupling to strong coupling in the same way that the BES kernel allowed that to happen for the cusp. But there are other places where we know how to go to finite coupling, but they're still for restricted kinematics. We know how to go to very strong coupling up here in terms of these minimal surfaces. And now we know how to perturb to reasonably high order for some classes of amplitudes using these bootstrapping techniques. And the grand goal is to get a finite coupling description everywhere in the kinematics. So that's sort of the general goal of this program of solving for planar n=4 super Yang-Mills amplitudes. But in the rest of this talk, I want to switch gears and discuss another observable in planar n=4, which is a form factor. And this is work that I did with Andrew McLeod and Matthias Wilhelm through 5 loops, and we're finishing up the 8-loop paper. And so it's very similar to the process glue to Higgs glue, which I mentioned is only known to 2 loops in QCD. And so we can compute its n=4 analog through 8 loops now. And in the QCD case, the highest order calculations are done by replacing the top quark by this operator here, H times these 2 gluon field strengths. In the super Yang-Mills case, we don't have single operators, we have super multiplets of operators. And these matrix elements of operators with plane wave gluon states are just generically called form factors. And in n=4, this operator is actually part of a protected stress tensor super multiplet. For example, you could compute with scalars instead of gluons initially by considering this representation of it too, if you want. Now, you have a choice of how many gluons to look at. And you might think that the simplest thing is to compute with 1 fewer gluon. That process is allowed kinematically, but it's actually too simple. It has no kinematic dependence because the only scale that it has is the center of mass energy of the 2 gluons, or the Higgs mass. And that factors out of the process by dimensional analysis, and everything else is constants. And so you can't kind of use the ability to move around in the function space to help you determine things. Instead, this form factor with 3 gluons is just right. It has 2 dimensionless ratios, and that's simple enough that you can explore it, and you can actually visualize the whole phase space. So the whole phase space for this process has just 2 independent variables, u and v. Now at the start, you have 3 momenta that add up to the Higgs. If you square this relation, you'll see that the invariant of these 3 gluons, S123, is just the Higgs mass squared, or the operator Q squared. But if you expand it out using the fact that the gluons are light-like, you'll see that it expands into 2 particle invariants. So if you then divide by this overall scale sort, you get 3 dimensionless variables that have to add up to 1. We call them U, V, and W. And sometimes we leave W in there because the dihedral symmetry that rotates these invariants around rotates U to V to W and so on. And the whole amplitude in the n equals 4 case, the one we're looking at, is actually invariant under this dihedral symmetry. So, but this is the general phase space. In here, we have a pseudo-Euclidean process where the Higgs decays to 3 gluons. Out here, we have scattering processes that are a little different depending on whether the operator, which I just call the Higgs for short, is space-like or time-like. If we look at the one-loop integrals, as I mentioned before, we just get these dialogues, and because they have dimensionless arguments, they can all be written in terms of u and v. And now I want to go back 10 years. So about 10 years ago, Thomas Germann, Nigel Glover, Matthias Jacquier, and Koukoutsakis computed this process in QCD at 2 loops, and they found a fairly lengthy expression by the standards of the day. And soon after that, Brandhuber, Travaglini, and Young, they did the analogous computation of the stress tensor form factor in planar n equals 4. And they found rather remarkably that what they got was much shorter, and it coincided with the maximally transcendental part of the QCD result. And this is kind of remarkable. It was known previously that certain quantities like Altarelli-Parisi or DGLAP anomalous dimensions or splitting kernels, which sort of depend on one variable, obeyed a similar principle that the maximally transcendental part of the QCD result coincided with n equals 4. But it doesn't happen for generic scattering amplitudes. So this particular process has some special role that goes beyond, that is more special than a generic scattering amplitude. Let me also mention that the function space that Germann and Remedi used to describe this amplitude, what they called it 2D harmonic polylogs, after some 1D harmonic polylogs of Remedi and Vermazerin, which we'll come back to. But you could describe this function space by saying that every function has a u or a v derivative that has at most 4 terms in it. And these quantities here are, again, 2D harmonic polylogs, just with 1 lower weight. And their prefactors are the appropriate derivatives with respect to u or v of the logarithm of something. And that something is listed upstairs. So that overall, there were 6 different quantities in the derivative. And this is a general property of classes of polylogarithmic functions that we'll talk about in a second. So if we want to try to build this function to higher loop orders, what we do is we take this function space and try to find the right amplitude within it. But in some cases, we find shortcuts or smaller subspaces of this, and we have to construct them to high weight. These, the more general setting that all of this structure is embedded into is a class of functions called iterated integrals. At least one version of it include G functions or Goncharov polylogarithms sometimes. And they're obtained by integrating a d log, where this a can be an arbitrary function of the kinematics over a previous set of g functions at one lower weight with one less index. So here the weight is n, and here it's n minus 1. Now, we can also define these polylogarithmic spaces differentially, which is a little more convenient for our purposes here. And you'll see that this definition coincides with this definition. If these d logs are logarithms of u, v, w, 1 minus u, 1 minus v, 1 minus w. But there's a very nice mathematical structure that exists for these generalized polylogarithms that maps them, sort of decomposes them or picks them apart. And in general, it maps a function to products of functions or tensor products of functions in the same space. Anyway, we don't need much of this bigger structure here. We just need to know that the derivative is one piece of it, and it maps it to two functions, one that has weight sets of functions, weight n minus 1, and one that has weight 1. So we call this the n minus 1 comma 1 coproduct of f, but it's just a way of describing the derivative. These SKs, we refer to them as letters in the symbol alphabet for the given problem. Once we've taken one derivative, we might as well keep doing it. And when we keep doing it, we can define things that are like the second derivatives, suitably defined, or double coproducts. And those are obtained in the same way. And if we keep iterating this, we find that the maximal iteration, which is n for weight n function, is the symbol. And so it's a tensor sum over many different d logs, up to n of them, with coefficients that are just rational numbers. And we often omit the logs and put these tensor product signs in B to define this symbol. So the symbol is important because this map, or writing backwards, is going to involve exchanging front and back of the symbol. But before we do that, let me just give an example or two. If we have the classical polylogs, you may recall that they were defined by integrating dt over t times the previous one. And many of you know that they have a regular series expansion, which is found by integrating up these series expansions. And so they're regular at x equals 0, and they have a branch cut at x equals 1. The fact that we have an iterated integration or iterated differentiation of d log, the derivative of this with respect to x has a d log of x in the back. And if we look at this rule, it tells us that we compute the first coproduct by putting an x at the back of the previous one. And if you iterate this, you find that the symbol of the classical polylog of weight n has n minus 1 x's at the back and then a 1 minus x at the front. And it's not an accident that the branch cuts start at x equals 1, where this thing vanishes. That's just a property of the initial integration. And then you have derivatives that are computed by clipping off the last entry. That d log x tells you exactly how to compute the derivative. So a nice way of encoding properties of the functions in the symbol is to say that you learn about the branch cuts from the first entry of the symbol, and you learn about the derivatives of the function from the last entry of the symbol. But these are fundamentally different types of processes, properties. Branch cuts and derivatives seem totally different. We can generalize the classical polylogs, and we need to describe most functions of one variables that you get from perturbative calculations. And so the generalization gives us the one-dimensional harmonic polylogs, and they are obtained by either integrating dt over t or dt over 1 minus t at each step. So you have two choices at each step for the harmonic polylogs, and there's a much larger number of them as a result. There are actually 2 to the 2L of them for the weight that we need for an L loop amplitude, which is quite a large number. And their symbol is computed by looking at the differential version, and we see that the symbol alphabet just has these two letters, x and 1 minus x, which are recorded by zeros and ones in this string of indices here. So just going back to the actual case for Higgs for this operator 3-gluon matrix element, because the functions look like this, we now read off directly what the letters in the symbol alphabet is. And there are 6 of them, the U, V, W, 1 minus U, 1 minus V, 1 minus W. Now you might be curious, what does this space look like? And it has a number of elements that include polylogs, classical polylogs, some certain true 2D HPLs, and a bunch of higher order ones, integrals, which I won't describe explicitly. But all the derivatives, in the sense of taking coproducts, have to land on functions that are lower down in the weight. And so this kind of generic structure is also true for any one of these symbol alphabets you might have, not just the one we were just talking about. In fact, if you look at n-gluon amplitudes for various values of n, we know something about the symbol alphabet. And in the 6-gluon case, I'm going to put hats over the U's to distinguish them from the form factor variables. But there are actually 9 letters for the 6-gluon alphabet, and 6 of them look very similar to the form factor case. And then there are 3 more, which are actually more complicated if written in terms of U hat, V hat, and W hat. And then things just get even more complicated as you go to larger numbers of legs. So the 7-gluon amplitude has a symbol alphabet with 42 letters in it. The 8-gluon amplitude contains at least 222 letters, and we don't even know if it's finite or infinite as the loop order goes to infinity. And when you go beyond n equals 8, you start encountering, well, depending on the helicity configuration, even more complicated functions. For example, at 2 loops and 10 points, you get functions that are definitely not in this polylogarithmic class we've been talking about, but involve singularities on elliptic curves. So they're called elliptic polylogarithms. At 3 loops and weight 12, there are certain integrals with singularities on a K3 surface, and there may also be other Calabi-Yau integrals that appear even earlier in the loop order and the number of legs. And so anyway, there are monsters lurking out here, very difficult functions to describe. But if we start with the simplest process that has any dual conformal variables at all, the 6-gluon process, we have a very closed system with a relatively small number of these symbol letters. Now we're going to start to hone in on this duality I was alluding to. And first, though, we're going to change the alphabet. It's an equivalent alphabet. It runs from A to F instead of U, V, W, 1 minus U, 1 minus V, 1 minus W. And it was motivated by some things we saw happening in the 6-gluon case. And when you change to that, then the symbol becomes much shorter. And the symbol at 1 loop and 2 loops is so short, I can even write it on the screen here. So the suitably normalized, I'm not going into all the details here, 3-gluon form factor at L loops becomes just 1 and 2 terms plus the S3 or D3 dihedral images. So at 1 loop, the symbol has a single term, which involves the letter B first and the letter D at the end, plus you have to sum over dihedral images to get a total of 6 terms. And the dihedral symmetries act like this in this A, B, C, D, E, F alphabet. And at 2 loops, you have only 2 terms plus the dihedral images. Now at 3 loops, you have 600 and something terms. So this was a little bit of a cheat. I'm not going to put that on there. But the point is, it's still a much shorter symbol because there are various restrictions that are much more apparent in this alphabet. So anyway, we can crank out results for these through 8 loops. And when we do that, we found that the simplest analytic region for this 2-parameter problem is to take one of the variables to infinity. And when we do that, we get these harmonic polylogs in the other variable. And if we use the right argument here, everything starts with a 0 and ends with a 1. But in between, you can get pretty much any sequence of 0s and 1s that you want. So we did this to 8 loops, and that one has 16,384 terms, which I'm not going to show you today. But then we remembered that back in the 6-gluon amplitude, we had done something similar. We found a line on which the amplitude was the simplest, and that line corresponds to choosing one of the cross ratios to be 1 and the other 2 to be equal. And again, we could write it in the same form. But then when you have like 2 sets of simple expressions, at some point in time, you stare at both of them at the same time, and you start to see they look kind of similar. You can see that all these coefficients up here, if we ignore the zeta ones, they're exactly the same. Now the strings are a little bit different, but we can map from one to the other if we just let 1 over v hat be 1 minus 1 over u. And that kind of corresponds to switching 0s and 1s. So we could switch the 0s and 1s here, but then this would be a 1 and this would be a 0. So then we should also reverse the string. So if you apply that map, you find that everything works out, and you can do it. And when I say at the symbol level, I mean ignoring these zetas here. It works to 7 loops. There are 4,000 terms that all exactly agree. Now this was just on a one-dimensional slice, but since then we found that it holds in a full two-dimensional phase space of the form factor, and this is what we call antipodal duality, because it involves reversing the orders of entries in the symbol, and this reversal has been called before the antipode map. So if we have one of these terms in the symbol, the antipode map says reverse it. Also multiply by -1 to the m, but for us, m is always even, so it doesn't really matter. And we also need a kinematic map. We have to know which point we're going to from the form factor to the amplitude. And the rule we found in the full two-dimensional phase space, these are the amplitude variables with hats on them, and these are the form factor variables. Now, there are really only 2 form factor variables, so there must really only be 2 amplitude variables. That is, we must be on some constrained surface, and this surface has a vanishing of this delta, and there are different ways of interpreting it. It seems like a good way to interpret it is something we call twisted forward scattering. So we're going to think about this for generalizations to larger values of n, but n is 3 here. And when we go halfway around the number of gluon momenta, we identify them with a minus sign. And that will automatically solve momentum conservation. But because we have a smaller number of vectors, it also puts us on a surface that has a Graham determinant constraint, which is precisely this one. So we live in some subspace of the amplitude, but it can be done everywhere for the 3-gluon form factor. So we can also ask, what does this do on the letters? And once again, it's better to trade to a different alphabet. These Y letters, by the way, they're rather complicated, but on this surface, they just die. Anytime you see a Y letter, you drop that term. So then we have the same number of letters again. We put hats over them to distinguish them from the form factor one. And now the kinematic map looks fairly simple on these letters. It just takes you from an A-type letter to a D-type letter and back again, but with a square root in one case. So we apply this map on the symbol, and we find that it works through the maximal order that we have on both sides. And that involves 93 million terms working right. So we think it's going to work to higher orders. And this map, it covers the entire phase space for the form factor side, and it lives on a surface inside the 3-variable space that I showed you before. The surface delta equals 0, it looks like this. Inside the unit cube, the portion of it that's there has these colors here that help you see that it's a fairly singular map in some sense, because this line here maps to this point. And if you study it further, you find that soft limits are dual to collinear limits on the other side, and collinear limits are dual to soft limits. These white regions also map, they just map outside of this unit cube, and we didn't show them for brevity. But another very interesting thing is that there are many special points that map into each other here, where the functions become numbers, and the numbers are polylogarithms evaluated at like unit argument with various roots of unity. In some cases, like at this symmetric point here, 6 roots of unity. And sometimes there are multiple zeta values and so on. And there's a very nice way to organize these numbers so that they're consistent with this coaction that I briefly mentioned earlier. And when you do it, then the antipode map is just supposed to reverse strings of arguments. We have this evidence at many different points, and this is evidence that goes beyond the level of the symbol because it involves zeta values that are wiped out by the symbol. At this simplest point, 111 in the amplitude side, which is out at infinity on the form factor side, we find that these blue numbers give us evidence of the duality. They multiply some quantities which are a way of encoding multiple zeta values and ordinary zeta values, and every time you reverse the string of arguments, you find the same coefficient. On the other hand, for things that have powers of I pi, which include pi squared, which is zeta 2 is pi squared over 6, and these are also proportional to powers of pi, we don't know what's going on. And there's sort of a reason for it, that half of the coproduct is really only defined mod I pi. But that's where we're at. If we ignore the I pi stuff, everywhere we check, we find agreements of this type. I mentioned finite radius of convergence. I just wanted to come back to that briefly. We have numerical values where we take the ratios of amplitudes and form factors, and this is just one example of it. It's the form factor on a symmetric line through the Euclidean region. And you see there's something kind of amazing happening here, where the ratio starts to flatten out. Away from these boundaries where there's some logarithmic divergences that depend on the loop order, everything starts to flatten out. And if we look at the ratios of successive coefficients here, and we compare them to the cusp anomalous dimension, they're within about 3%. So this thing, although it's far from where the cusp has something directly to do to it, behaves very much like the cusp across this broad range. Eventually, the ratio should go to -16, but the cusp takes a long time to get there too. Lurking behind all of this is a flux tube description at finite coupling that was worked out by Basso, Sever, and Vieira. I don't really have time to say much about it, but there was a similar one for the form factor that was much more recent, just in the past 2 years, and it was a key ingredient in bootstrapping these form factor amplitudes. All I want to say is that there's a parameterization of this from the operator product expansion approach, which seems to have something important to do with this duality, although we don't fully understand it yet. When we write the amplitude variables and the form factor variables in the appropriate OPE parameters, we find that the map between the two becomes very simple. And it just looks like this. And it seems like it may be telling us that single flux tube excitations for the amplitudes are supposed to be mapped to double excitations for the form factor. But in order to really understand this better, we need to go further beyond the 6-gluon, 3-gluon form factor duality. So we've been working also with my student Andy Liu on the 8-gluon, 4-gluon form factor. And we have some candidate for how this works. We also know a 2-loop amplitude on one side, and we're mapping it to a symbol on the other side because this side hasn't been computed directly yet. And so we're trying to see if this duality really gives us the right answer, and that's still in progress. So I'll skip now to the summary, which is that due to the remarkable properties of planar n equals 4, some of the simplest form factors as well as scattering amplitudes can be bootstrapped to 7 or 8 loops. we find remarkably simple analytic behavior in some regions, one of which is the origin of the 6-gluon amplitude. And when we compare the form factor to the 6-gluon amplitude, we find this strange new antipodal duality, which swaps the roles of branch cuts and derivatives as it exchanges the order in the symbol. So to us, this is extremely weird, and we don't understand it at all, what the physical origin is, although we have great quantitative evidence for it. So we'd like to go further and understand this physical reason for the duality. It suggests there should be some things happening at strong coupling, which could be tested through the minimal surface approach. And we'd, of course, love to verify it better at this 8.4 level and exploit it to learn more deep things about amplitudes and form factors, at least in planar n=4 super Yang-Mills. So thanks a lot for your attention, and I'll stop there and happy to take any questions.
Thanks a lot. And yes, whatever questions and comments, now's the time. I want to thank you for this, telling us about these exciting results, but also for the panorama, big panorama view, which was very interesting. Yes, David Broadhurst. You can unmute yourself.
Hey, David. Unmute.
You should unmute. Yes.
Unmute yourself, David. Still muted. There we go.
I wasn't allowed to unmute myself.
Oh, sorry.
I was being censored. So suppose you have, as you do to a given loop order, the complete analytic expression for the 6-gluon case. It seems to me you still can't go on your surface to the 3-gluon amplitude because you have ambiguities which are not picked up by the symbol. You have products of harmonic polylogarithms times zeta values. So one does not imply the other, but they share a certain structure. Is that right?
So we have more agreement than just the symbol. If we take the coproduct, we find that everything with a zeta 3 works.
Right.
To as many loop orders as we could do it.
Okay.
We can do it on lines all the way to 7 loops. We can do it in the bulk to about 3 loops before the computation just gets too long. But we don't have everything. Anything that has an I-pi in it or an even zeta value, we don't know what to do about it.
But that's an old problem. That's a problem that Goncharov had at the formal level and Francis eventually solved.
Yeah. So there's also a physical issue with these I-pis, because as you know, when you move from one sheet to another, you get I-pis. And we don't know what sheet we're supposed to be on, is the short way of saying it. And we have issues with the various sheets we've tried. Like one sheet we try, on one side it stays real, but on the other side it becomes imaginary. If we let it go imaginary on the other side, it diverges in one place where it's not supposed to on the other side. So anyway, I think the resolution to this, if there is one, will be that you have to understand the sheet structure very well.
Thank you.
Thank you. Other comments or questions? Should be free. I will ask a very down-to-earth, a very basic questions. If this symmetry is there as it look like, well, I call it a symmetry just because it should hide a symmetry. So what do you? It's your last question. The exploitation of it means using it as a constraint, and can you? It's easier to calculate.
Well, there's one very obvious way to exploit it, which is, you may have noticed we have the form factor to one loop order higher than we have the amplitude.
Exactly.
So the symbol of the 8-loop form factor has 1.6 billion terms. So I was able to write them out and switch the order of them. And that gives us the symbol of the amplitude on this 2-dimensional surface. So I gave that to my graduate student because he's very good. You just hand him 8 loop problems and you can eat them up, right? So anyway, his job is to lift that into the bulk. And you can ask, how ambiguous is that? And it turns out that through 5 loops, there's no ambiguity at the symbol level. It uniquely determines the symbol. At 6 loops, there's 1 ambiguity. And at 7 loops, there's also 1 ambiguous function. And strangely, we had seen these functions before when we were bootstrapping the amplitude without this information. But anyway, there'll be a very small number of ambiguities, and then you can use all the standard limits that we used before to fix all the coefficients. I'm sure it will be straightforward to do. But the first question is to lift it off the surface in a unique way. That's the hard step. Anyway, that's kind of a simple way of or not simple, but a very concrete exploitation. But we will, in the cases with more legs, like this 8-4 case, you want to go the other way, because we have a little more data on the amplitude side than we have on the form factor side. In that case, we actually know the 8 gluon amplitude for this MHV configuration to 3 loops, thanks to work of Li and Zhang last year. So we're taking their 3-loop symbol, we're applying our candidate map as well as the 2-loop symbol, which Simone Carenhua computed about a decade ago. And we're hoping it gives a sensible answer, but we haven't completely confirmed that yet.
Oh, that's great. Are there other comments, questions? Yes, Yuri. Yes, please go ahead. If you can't, I'm not sure how.
Hi, Len.
Hi, Yuri.
Hi, thank you for this absolutely exciting talk. I mean, I'm just trembling. Look, I wanted to ask you a rather philosophical question. Let's say.
Sure.
Have you thought about why on earth n=4 planar is so friendly?
Yeah.
Because I can just give you my thoughts straight away. To me, it looks as if it were a dream of Francis Lowe, because there is pure self-interacting classical fields with no quantum corrections to it.
Uh-huh.
Have you thought in this direction? Because, I mean, you look at anomalous dimension, you look at beta function, you see no quantum fluctuation, just Lehner-Wichert potentials everywhere.
Yeah, that's an interesting way to think about it. I mean, I think there's a sense in which large N theories in general are classical. You know about this? Like, I mean, back when I was a grad student at Princeton, Larry Yaffe had a program of trying to compute large N hadron masses by the Migdal-Makienko equations, but in a classical phase space.
Yeah.
And so I don't know all the details of how large N classicalizes and what additional things you need for large N QCD to fail to be as nice, but certainly thinking about things from a classical perspective is a very interesting one.
Thanks.
There's also, connection where you make connections between n=4 and QCD. It works best in infrared quantities, the DGLAP kernels or even more special things like cusp anomalous dimensions, collinear anomalous dimensions.
Sure.
They sort of satisfy this transcendentality principle in a way that doesn't happen for a generic observable. And maybe those things are also more classical in some sense. I don't know.
Right.
Great question.
You see, I mean, what was my point is that, I mean, you just look at, I mean, you take good old Francis Lowe paper, right? And you look at anomalous dimensions in your Parton evolution, whatever, and you see that everything cancels but this your logarithmic psi function, right? The whole anomalous dimensions first loop is just pure psi function with no quantum effects left. So it's pure Fourier transform of Lehner-Wichert according to Francis Lowe theory.
Yeah, it's true that this whole flux tube story is heavily based on the psi functions.
Absolutely.
And for example, if you go back to this picture of the surface here, this line here is near where the flux tube expansion takes control.
Mhm.
And in here, every time you expand a function around here, you get ordinary Riemann zeta values. You never get multiple zeta values in this region. And that's a reflection of these psi functions kind of controlling everything.
Mhm, mhm.
Now out here, you're very far from there and you have to resum things. And when you look here, you get true multiple zeta values.
Right.
But it's sort of because you're resumming a lot of these flux tubes, I guess, to get there.
Sure.
I don't know how to blend that with your picture, but definitely be
Yeah, I see.
interesting.
You see, it obviously doesn't mean that the theory is simple or empty, not at all, because it's still
Yeah.
self-interacting classical fields, but classical, there's something in it, I guess.
Very interesting. Thanks.
Thank you very much.
Thanks, Yuri Doxischer, for the nice comment. Are there other questions or comments? I wanted at page 46, which is the other one, the next one.
Yeah.
Is there, did you write it well, or it's plus minus, for example, A46, F34, I see, so you only underline in blue the things which match,
Yeah.
and the other do not, and we don't care. Can you repeat why? For example, there is a minus.
Actually, you know,
plus.
you noticed this minus sign, I guess. I need to go back and check that I didn't do a copy paste mistake.
Okay.
Because this looks too good to be true. I think it's probably wrong. The point is that as far as I know, everything that has a zeta 2 in it or more, or a zeta 4 or a zeta 6 is screwed up.
Yeah.
And so I'm guessing this is just a copy paste mistake.
Okay.
I'll go back and let you know.
Okay, thanks.
But the main point is that everything that has a in blue, at least I seem to have gotten the signs of those things right.
Thanks.
By the way, there's typically a numerical alternation in sign that happens for the total answer all the time.
Like for the cusp.
Yeah.
Isn't it?
And if you look at the numerics here, you see everything's negative. When you go from one loop order to the next, everything's always negative. But when you start staring at an analytic representation of some of the answers, there are different signs. And it's generally true that these very interesting analytic pieces, the multiple zeta value parts, are not always the biggest parts. They're often the pi squared parts. There is some question of what this duality means in terms of numerics, since the I pi's are out of control. I think I have a slide here that maybe sheds some light on this. This is the same slice that I was showing you, the successive loop orders for the form factor in the from one loop order to another. Now I'm taking the ratio of the numerical values of the amplitude in the Euclidean region to the form factor in the denominator with the right normalization. When I say the right one, I mean it automatically agrees exactly at each loop order at these two endpoints, which are these soft collinear limits. But in the middle, the pi squareds and the fact that the antipodal value of a polylog is not numerically equal to a polylog, things change. But they change by at most about 1.6 for whatever that's worth. Whereas each term from loop order to loop order is going up by minus 14 or something. So anyway, this is just an illustration of the fact that these functions are numerically not too far off, but also not identical.
Thanks. Other comments or questions quickly? Yes, there is someone. I saw a hand, but maybe I was wrong. Yeah, maybe I was wrong.
I don't see any.
Okay, good. Okay, so then I leave it to Stefania to thank
to
again
thank,
Lance.
to really thank you for this wonderful summary and prospect for. Okay, no, this is only a clap. It's not a hand. Hand. So thank you very much, and please send us your slide.
I will.
And we'll publish them. And I want to thank also all the audience for this meeting, and wish you a very good evening, night, or day to you. Okay, see you for the
Thanks
next.
a lot, Stefania and Valentina. Bye.
Ciao a tutti.
Goodbye. Bye. Thanks a
Ciao,
lot again.
bye.